Good morning, gentlemen. Today is Wednesday, May the 27th, and today we are going to cover the last day, the last section of our lessons on geometric optics, lenses and mirrors and whatnot. Um, so for tomorrow, Thursday, May the 28th, we will be having a review activity on geometric optics. And I will at your regularly scheduled class time, I will send out a couple of questions, and I expect that you'll answer them to the best of your ability within 30 to 40 minutes or so. Now, today, we're going to concentrate on curved lenses, but more specifically, we're going to talk about the formulas for curved lenses. Just like with curved mirrors, the formulas relate focal point, distance of the object, distance of the image, as well as the size of the object and the size of the image. The nice thing about the formulas is that they are exactly the same as the formulas for curved mirrors. All right, you'll notice here the one that just popped up on the screen. 1 over the focal point is equal to 1 over the distance of the object plus 1 over the distance of the image. Excuse me. And the second formula, of course, is the ratio of the size of the object to the size of the image is equal to the ratio of the distance of the object from the lens to the distance of the image from the lens. Now, a couple of things that I do want to point out before we get into some example problems. In this case, the focal point is going to be negative for concave or diverging lenses, whereas it's going to be positive for convex or converging lenses. All right, so keep that in mind when you're doing your math. I've noticed that several of you with the curved mirrors homework assignment have been forgetting that the focal point is negative for diverging objects. The distance for the object is always going to be positive, all right, because obviously the object is going to be sitting on the positive side of the lens, wherever you're starting from. And the distance of the image is going to be positive for real images, in other words, ones that are formed by 2 light rays coming together, but negative for virtual images, images that are formed by the apparent convergence of the various light rays. All right, so here are the formulas. Remember that the formulas themselves are not found on your handy dandy reference tables. So if you've not already taken the opportunity to write them down in the waves section of your sheets, please do so as soon as possible. All right, so that for tomorrow's review activity, you'll have them right there in front of you and ready to go. All right, okay. Now, moving right along then, let's go to example number 3. And example number 3 is going to deal with curved lenses. Specifically, we're going to deal with a converging lens, all right? And so in this case, we've got an object that is 0.03 meters tall. So obviously, notice here the height of the image is given in meters, so there's no need to convert anything, at least not yet. So 0.030 meters tall is placed 0.050 meters in front of a converging lens having a focal length. All right, so let's start here. We've got our converging lens. Oh, that's a fat lens. Okay. And we'll draw our principal axis right through the middle. We'll place our center here. This is the center of curvature, or sometimes called 2F, 2 times the focal length, because the focal length is going to be located here. Now, we know that the focal length is 0.04 meters, and the object is placed at 0.05 meters. So the object is going to be located here. Now, let's draw the focal length on this side over here, over yonder. And the center of curvature will be, I don't know, maybe here. We'll call that C, or again, 2F. Now, if we send a couple of light rays through here, what's going to happen? Well, we send this one through. It then converges right through the focal point. We'll send another one right through the center of the lens. And in this case, it's going to, going to move through the center of the lens and just keep going straight. And this picture is awful. All right. In this case, what should happen is that they should meet out here somewhere. So I've screwed this picture up. Sorry, but the image should be located out here somewhere beyond 2C. All right, or 2F rather. All right. So in this case, let's go back to our information. And so in this particular case, I have whoa, what is going on here? So the size of the object, S sub O, is going to equal 0.03 meters. All right. And because this is so difficult to write with a mouse, I'm going to just skip the sig figs and that kind of stuff. Distance of the object is 0.05 meters, and the focal length is going to be 0.04 meters. All right. So the first thing we got to do here is to describe the image. All right. And in this case, the image is going to be a real image. All right. It's projected outside of the lens, so it's real. In terms of its size, the image itself is going to be larger than the object is. All right, and in this case, it's going to be inverted or upside down. Okay. Now, determine its position. So we're looking for DI here. Come on. And so I know that 1 over F equals 1 over DO plus 1 over DI in this case. All right. And so here, 1 over DI is going to actually equal 1 over F minus 1 over DO. All right. So here, that's going to give me 1 over 0.03. Nope, I lied. 1 over 0.04 minus 1 over 0.05. All right. And doing a quick bit of math, that's going to give me a DI value of, let's see, get out the handy dandy little magic number box. 1 divided by 0.04 minus 1 divided by 0.05, and that's going to give me, actually it gives me exactly 5, but 1 over that will give me 0.2, okay? And so the distance of the object is going to be 0.20 meters. Oh, come on. Okay, 0.02, I'm sorry, 0.20 meters. All right. Now, does that make sense? Is the distance of the image further? It should be located out beyond point C. Well, point C is 2 times the focal point. The focal point is 0.04. 2 times the focal point is 0.08. So 0.2 meters out is certainly further than that. Now, in order to calculate the value of SI, I'm going to say that SI is going to equal, or SI over SO is going to equal DI over DO. And so SI is going to equal DI times SO over DO. Okay. So in this case, SI is going to equal DI, we just calculated as 0.2. I'm going to multiply that by the size of the object, which is 0.03, all divided by the distance of the object, which is 0.05. All right. And so doing a quick bit of calculation here, that's going to give me 0.2 times 0.03 divided by 0.05, and that gives me 0.12 meters. Okay, so the size of the image is going to be 0.12 meters. All right, now the size of the object was 0.03 meters, so this is about 4 times bigger. Does that make sense? Well, we said that the image was going to be larger than the object, and so yes, this does make sense. Okay, now, if there are any questions about this, please let me know. Now, in terms of the next, example number 4. All right, same kind of question here. As a matter of fact, everything's going to be the same except for the numbers and the fact that this time we're going to work with a diverging lens as opposed to a converging lens. In this case, matter of fact, I'm going to keep the numbers pretty much the same. An object 0.030 meters tall is placed 0.05 meters in front of a diverging lens. All right, so let's draw our diverging lens. Not a great job, but we'll deal with it. And so I'll place my, here's my focal point. Twice that distance is my center of curvature. Focal point and center of curvature out here. Or remember, center of curvature is 2 times the focal point. Now, so the object itself has, again, the same characteristics. So the size of the object is going to equal 0.03 meters. The distance it is in front of the lens is going to be the distance of the object, and so that's going to be 0.05 meters. And the focal length of the lens in this case, f, is going to equal 0.04. meters. Okay. Now, in this case, remember that because it's a diverging lens, this focal length is going to be negative. All right. Now, what happens here? Well, the object is going to be placed, the focal length is 0.04. So this distance from here to the vertex is 0.04. The distance of the object is 0.05. So the object is actually located a little bit further out. So it's about here or so. Now, if you send a light ray, what is going to happen here? Well, the ray of light, come on now, is going to come through here and diverge like so, such that the light ray appears to have originated at the focal point. Okay. And the second light ray I'm going to send right through the middle of the lens, maybe like so. And so what that's going to do is it's going to give me an image here. Okay. Now, this is going to be a virtual image, not real. Okay. It's going to be smaller than the object. And it's going to be right side up or erect. Now, we're asked here to figure out its position. And so I'm just going to go right ahead and rearrange the formula without writing it all out. But 1 over di is going to equal 1 over f minus 1 over do. In this case, it's going to be 1 over negative 0.04. Whoops. Minus 1 over, the do value was 0.05. A little bit of quick arithmetic here. This is going to be 1 divided by negative 0.04 minus 1 divided by 0.05. And that's going to give me negative 45. But if I take the inverse of that, so 1 divided by negative 45, that's going to give me negative 0.022. Okay, so the di value is negative 0.022 meters, just in terms of significant figures. Now, does that make sense? All right, it does. All right, because we know that the distance of the image is going to be on the same side as the object, and so and closer to the actual lens. So the distance of the object was 0.05. The distance of the image is going to be negative 0.022 meters. Now, let's look at the size of the image. In this case, that's going to be SO times DI over DO. Now, the size of the object is 0.03. The size of the distance of the image is negative 0.022. And the distance of the object from our laundry list is 0.05 again. And so that's going to give me a size of my image, let's see, of negative 0.022 times 0.03. Don't forget, don't round the negative 0.022. And then divide the whole thing by 0.05. And that's going to give me negative 0.013. All right. And in meters. All right. And so there are my answers. Okay. Sorry about all of the mess here. All right. But notice that both the distance of the image and the size of the image are negative. All right. Okay. Moving right along. This is just kind of a little bit of an aside, but I do want you to be aware that the principles that we've been talking about here are very important for those of us who wear glasses. All right. There are three major kinds of issues with your lenses, all right, the lenses in your eyes that could lead to you wearing glasses or contacts. All right. You can be nearsighted, you can be farsighted, or you can have an astigmatism. All right. And this slide shows how glasses, well, first of all, show what the problem is, and then how glasses can actually change and fix your vision. So if you are nearsighted, what that means is that your eyeball is actually a little bit longer than it should be. It's a little bit more elliptical or elongated. And so what happens is the light rays come in from a great distance. So
it's 10 o'clock.
Oh, thank you, Jesus. So things that are very far away, the light rays come in parallel and they are focused on a point right here. But that's not your retina. Your retina is actually located along this area. All right. And so the focal point is not on the retina. And you can't see things that are very far away. That's why we call you nearsighted. So if you take a diverging lens in this case, then what happens is that the parallel light rays come in, they diverge, you can see them spreading out here, before they hit your lens, and then your lens converges them on the appropriate spot in the back, right here. And so you can form an image. On the other hand, if you are farsighted, that means that things up close, where the light rays are coming in from something very close, are converging at a point that is past the retina. So again, here's the retina-ish, all right, and you're focusing beyond them. All right. In order to correct this to form a clear, sharp image, you use a convex or a converging lens. So the light rays come in, they're converged by the glasses, then they're converged again by your eyeball's lens, and the image forms right on, or the focal point is right on the retina. Now, astigmatisms are a little bit different, and it depends on what's going on with the astigmatism, but an astigmatism is essentially a lump in the cornea. You can see it drawn here in this particular example. But it could also be a problem with the lens itself, your eyeball's lens. And in order to fix that, what they do is they build you a set of glasses that has a matching contour of the astigmatism that you have in your eye. All right. And that fixes, that causes, again, the light rays to focus properly exactly on your retina. Okay. For homework, please do the questions on the geometric optics homework sheet, numbers 3 and 4. All right, and if you get these done this evening, all right, they're not going to be due till tomorrow at the end of the day. But if you get them done today, I will correct them and give you some advice for your review activity on geometric optics tomorrow. All right. So happy Wednesday, boys and girls. I will talk to you later.